Hello again. We are going to continue our revision and going to go over the stability criteria according to Routh and Hurwitz. Well, the two guys discovered the same concept at the same time, so they were both credited with the concept. However, from now on, I'll just refer to it as Routh for simplicity. I don't know about the proper pronunciation. Some colleagues pronounce it as Routh. Anyway, you know what I mean. So, what is the stability criteria? First of all, the stability criteria gives us essential conditions, necessary conditions for the system to be stable. If these conditions are satisfied, we continue and investigate further. If they are not satisfied, we stop there and then and we declare the system unstable. So the first part, which is the necessary conditions but not sufficient, that all coefficient of the characteristic equation must exist from an, and so on, and all the coefficient need to be positive. If any one negative coefficient, then the system is unstable. These two conditions are necessary but not sufficient. For example, if we look at the first system here, this system S square, we'll have here that's negative, so that's not stable. This one here is 5, 4, oh well, there is S3 is missing, so that's also not stable. Here the coefficients are all positive, none is missing, so that's further investigation, further study to see whether the system is stable or not. So we will give the Routh array, and then from that, how can we find whether the system is stable or not? Consider the characteristic equation of the system. What is the characteristic equation? Remember Mason's formula. Mason's formula, we had the transfer function is sigma pi delta I over delta. This is the characteristics equation. How did we get this characteristics equation? The characteristic equation was 1 minus loop gains, the sum of the loop gains, plus sum of non-touching pair of loops, and so on. So from Mason's theorem, we find the characteristic equation. Then we will arrange the characteristic equation with the even coefficients in the first row, the odd coefficients in the second row. And this is demonstrated here. So I start an minus 2, and so on in the top row, and an minus 1, an minus 3, an minus 5 in the second row. From there on, I can construct the rest of the array. How? Remember, these two rows, I got them from the characteristics equation. And I can go to the change, just make it blue. The first two rows got them from the characteristic equation of the system. Now, how can I find this part here? This I can find it by all the third row will have one common element, which is this one, is the pivot. Basically, the first element will be multiplication of these two elements minus multiplication of those divided by the pivot. So that's P n1 is an minus 1, an minus 2 minus the product of an and an minus 3, all divided by an minus 1, which is the pivot. Then the second element will be obtained I just changed the pen color. I will go for something like I'm not sure how this is going to be. It's still blue. The pivot is the same, but we'll multiply an minus 1 with an minus 4 minus this multiplied by that, and all divided by the pivot, which is still the same, and so on. And that's, you get here the second element, bn minus 3. An example, straightforward example. Here we have the characteristic equation. First step first. Any missing coefficients? No. Any zero coefficients? No. Okay, we'll carry on. We will take the coefficient here is 1, it goes there, 3 goes there, 1 goes there, this 4 goes there. The remaining coefficient, odd coefficient, form the second row. So we form these two rows. Then the first element here, the pivot for all the third row is going to be this 4. The first element will be 4 multiplied by 3 is 12, minus 1 multiplied by 2, which is 2. 12 minus 2 is 10, divided by 4 is 5 over 2. The second element here, again, this will be the pivot. It will be 4 multiplied by 1 is 4, minus 1 multiplied by 4 is 4. 4 minus 4 divided by 4 is 0. The third element, again, this is the pivot. 4 multiplied by 4 is 16. 16 minus 0 remains 16. Divided by 4 gives 4. So on. The following rows, if we start here, the fourth row, the pivot for the fourth row, this will be the pivot. And the first element here will be 5 over 2 multiplied by 2 is 5, minus 4 is multiplied by 0 is 0. So that's 5 divided by 5 over 2 gives 2, and so on. We will end up and we find there is a change of sign here. How many change of signs? Be very careful. This is positive, 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 negative, positive. So how many times the sign has changed? From positive to negative is once. From negative to positive is the second time. So in this case, the first column, we had 2 sign changes. And because there are 2 sign changes, then we can conclude that the system is unstable, and actually has the characteristic equation has 2 roots, or the system has 2 poles in the right hand side, and because of that, of course, it will not be stable. Anyway, we carry on and take another example that's a bit tricky. This is a special case where we carrying on, well, got this from the characteristic equation, then started building the third row. This is the pivot. 2 multiplied by 2, 4 minus 4, 0 divided by 2 gives me 0 here. Then how can I continue? Because to construct the fourth row, this 0 will be the pivot. I cannot divide by the pivot, which is 0. What do? We replace the 0 with a small epsilon. We substitute the 0 element with a small number, carry on computation, and then afterwards see what happens when epsilon becomes very small, goes to 0, the limits when epsilon goes to 0. So if we carry on calculating, we find that C1 will be epsilon multiplied by 4 minus 12 divided by epsilon. Yes, that's 4 epsilon minus 12 over epsilon. When epsilon goes to 0, that will be minus infinity. Then C2, well, that's C1. D1 here will give me this coefficient, and then when epsilon goes to 0, gives 6. So this will be minus infinity, and that's will be 6, and that's when epsilon goes to 0. So how many sign changes here? Again, the system is stable with 2 poles on the right hand side. Another special case, which is a bit more tricky. We have this characteristic equation. We look at it. All coefficients are there. None of the coefficient is missing and none is negative. So we construct the array. Construct the array first 2 rows from the characteristic equation. Then this element here, 2 multiplied by 4 is 8, minus 8 is 0. The second element, of course, we have here 0 and 0. It will be 2 multiplied by 0 is 0 minus 0 gives 0. So we have 1 row of zeros. What do we do in this case? In this case, we go back to the last row, which is non-zero row. And last non-zero row is this one here. And we construct an auxiliary equation. Construct an auxiliary polynomial, coefficient of the previous row. So that will be 2s squared plus 8, or expressed like that. And this is our, anyway, this is our auxiliary polynomial. Differentiate the auxiliary polynomial. If you differentiate A, you will get 4s plus 0. Then take that 4 and put it instead of the first 0. So that 4, we'll put it there, which I'm doing in the other table. Construct the table. And if you construct the table, you end up with an array. Look at the first column. Is there any sign change? No. So although we ended up with a very strange situation that all the rows are 0, we ended up with a system that is stable. Actually, when you solve this auxiliary equation, it will give you S equal to J minus 2, J plus 2. So in fact, you will find that this system has 2 poles on the imaginary axis at plus 2 and minus 2. And this is the condition when the system is at the edge of stability. So that's plus 2 and minus 2j. So we know from Routh array that when we end up with rows of zeros, that rows of zeros indicates symmetric poles, of course, on the imaginary axis. And that means the system is at the edge of stability. Stable, but at the edge of stability. Which is very useful because in some design problems, you will need to find the value of k, or you need to find the intersection between the root locus and the imaginary axis. And the way to do this would be to find the rows, to force in the array to find the values that gives you rows of 0. Rows of 0 means poles on the imaginary axis. We'll look at another example, very useful example. Here, one application, very useful application, is to find the value of the gain for which the system is stable. So from here you find delta. Delta is 1 minus loop gain, and that will be 1 minus, and there is minus here, so it will be 1 plus k multiplied by s plus 1 over s plus 1. That's actually, this is minus 1 and s plus 6. Where did I get this from? I got this from Mason's theorem. So this equals to 0 is my characteristic equation. Simplify and then construct these first two rows here are from this equation. Then construct the rest of the array. For the system to be stable, we need to have no change of sign in the first column. So no change, we don't need any change of sign here. So this has to be positive and this has to be positive, which means the system can be stable if this part is greater than 0 and the k is greater than 0. And when you solve, it will give you k greater than 7.5, which is obviously greater than 0, i.e. this is the condition that gives you system stability. This is yet another useful application of the Routh or Routh or Routh-Hurwitz criteria. Good luck.